Hello Velociraptors and welcome to my classroom. Today we're going to talk about significant figures. Now when we talk about significant figures in this course, we're not just talking about numbers that you see in your course pack or numbers that you see in problems. Significant figures are associated with any measured value provided. And that measured value provides you a little bit of insight or actual insight into the accuracy of how that value was actually measured. So in order to illustrate that for you today, I have two solutions or samples in front of me. One here on the left, which is measured using a graduated cylinder, and the one here on the right measuring using a beaker. And I want to actually read the measurements to show you how we would correctly note significant figures using a measuring device. So let's take a look at the graduated cylinder. If we look at the graduated cylinder, we see that we have graduations every 1 milliliter. That means that every tick mark is indicating a milliliter of fluid. That is an exact value, and it's provided by the graduated cylinder. So if I notice this fluid here, it doesn't really have as much of a meniscus as we would see. That's where it adheres to the sides of the glass. We can see that it looks like this fluid is almost exactly on 52 milliliters. Now that might be fine. Sometimes it might exactly appear there. Or you might be seeing that it reaches just a little bit of a hair past that tick mark. As you can see that fluid, but that's probably it adhering to the glass. In this case, I would probably record that as 52 milliliters, but I need to include a decimal place. So it should be 52.0. And the reason for that is because if the liquid would have appeared in between two of those lines. So let's say if I looked at it and I noticed that maybe the angle I was looking at it, I had my head tilted a little bit and the liquid is actually a little bit above that 52 milliliter mark, I could actually guess to the 10th place with relative accuracy what the volume of the fluid is. So in terms of the graduated cylinder, I should be able to measure it to the 10th place. Okay, great. That's the accuracy of the graduated cylinder. Let's look at the accuracy of the beaker. Now, if I look at the beaker, we can see that the fluid is somewhere between 50 and 100. Now, in terms of my graduations, the tick marks this time, we see that I have a tick mark every 25 milliliters. So it's just above the 75 millimeter mark. Now, I have no idea how close it is above 75 milliliters. So I might guess, let's see, maybe, let's see, 75, 100, maybe 85-ish. 90-ish milliliters, but you notice that I'm saying 85 and 90-ish milliliters. I should only record probably to the 10th place, given that the accuracy of this beaker is not as good as the graduated cylinder. So I wouldn't write down 85.1 milliliters because that would be ridiculous. That would make it seem like the beaker had the same accuracy as the graduated cylinder. And you can clearly see it's much harder to read how much fluid I have in the beaker. That's significant figures. Significant figures are about the actual accuracy of the measuring device you're using. Let's walk through a few examples using measuring devices and seeing how those significant figures play out. So in front of me here, I have a Bluetooth speaker of mine. I want to use it because it has a relative uniform shape. And I want to use it to measure the volume of this. Now, in order to calculate the volume of this, I'm going to need some measurements from this device. I'm going to need its length, its width, and its height. So I want I want to show you how to properly measure that using a measuring device. So here in front of me, I also have a ruler. And I'm going to use this ruler to measure the length, width, and height of this device in centimeters. So in order to do this correctly here, I'm going to line it up on the left-hand side to the right-hand side. Now you should see a zoomed in image of this now. If you look here, we can see that the actual speaker is roughly pretty close between 15 and 16, pretty close to 15 and a half. Now there's a tick mark every centimeter. That's the dark ones, 1, 2, 3, 4, 5, 6, 7, 8, that's a centimeter. So the dashes in between, the tick marks in between are representing a 1/10 of a centimeter. So this is roughly 15 and a half, but it's not quite a half. I'm gonna say it's right in between a half. 15.5 and 15.4, so let's put 15.45. So let's record that measurement here. I've got me a little table. So 15.45 centimeters. is our length. Now let's go ahead and measure the width. I'm going to do it this way. Again, you're going to see a little zoomed in picture so we can read it correctly. Now I'm looking and I'm noticing that it's right between 5 and 6. Whoops, I didn't get it all the way. It's right between 5 and 6. It looks like it's actually past 5.5. So I'm going to put 5.6, and it's right on the line, so I'm going to put 5.60. Now make sure that you write 5.60, not 5.6, because we have to include all the significant figures provided by the measuring device, which is always one past the tick mark. That's our uncertain digit. Now, for some reason, let's say I lost the ruler. We have no idea where it went, and I need to measure the actual height of this speaker here. Now, when I measure that, I'm going to get that it's 2.4 centimeters. Now, quickly, you can see that the accuracy of the measuring device that I had was not the same. It's a little bit less than the accuracy. It's 1/10 less of a place accuracy compared to the length and the width. And that's going to come into play when we calculate the volume. So let me put this over here. And now we know that the volume is calculated by length times width times height. So volume, length times width times height. If I sub in those values, I get that it's 15.45 times 5.60 times 2.4. That would give me the volume. Now, I want you to pay attention. If you put that in your calculator, you're going to get this answer. Now, this answer is great, but it has a lot of assumptions based with it. First, this has 6 significant figures, meaning that, and it's recorded to the thousandths place. So if I wrote this down as my answer, I want you to be mindful that that means that what I use to measure it could measure up to the accuracy in the thousandths place. So the uncertainty is in the thousandths place. Well, you just watched us measure using the ruler, and it has more accuracy than whatever this unknown object was measured with, which means my answer cannot have that much certainty in it. It has to have the least amount of certainty present in my measurements. So in terms of this, I multiplied all my values together. The multiplication rule for significant figures is the least number of significant figures in your multiplication. So this has 4, this has 3, because that 0 does count, and this one has 2. So I need to record my answer to 2 significant figures. Now, in order to do that for 207, I can't just write 200 because 200 has 1 significant figure. If I put a decimal place on it, then it would have 3 significant figures. So I need to convert this from ordinary notation to scientific notation. So for this answer, I need to write 2.1 times 10 to the second centimeters. That includes the correct significant figures for the volume and ensures that I'm not providing a measurement that's more accurate than what I actually measured in terms of it. Let's work another one. For this example, I want to go back to those first 2 liquids that we had in the beginning. Let's say that I wanted to add those liquids together. Now, I recorded the measurements earlier and we talked about it together. And if we use the graduated cylinder, we measured 52.0. And then in the beaker, we measured 85 milliliters. This illustrates another example. So if I wanted to add those together to get my measured value in total volume, I would say that it's 137 milliliters of that purple liquid. Now, I want you to pay attention to significant figures here. The significant figures from the graduated cylinder say to the tenths place. The significant figures here say to a whole number. Now, in order for us to record this number correctly, it should have the same decimal places as the least significant answer. So this has 1 decimal place, no decimal place. So then my answer should have no decimal place. Now, of course, it was relatively easy in this case because both tenths place were blank. If this was 0.1 though, and I got 137.1, that would be incorrect. I needed to record 137 because I should only record to no decimal places because that's the least significant measured value. Let's try one more. Okay, our last example. Here I have a bike pump. Now I know, a little crazy. He's throwing a bike pump on here. But it's definitely an applied method. So I might use this to measure the tire pressure that's in my bike. Now, I also see that this is also, again, another type of measuring device. And you can see that I have increments here of various different pressures. Now, we're going to ignore the bars on the bottom. We're going to measure in PSIs, which are those top values. Now, let's say that that red ticker bar or indicator goes up here. You can see that in terms of marks, I have a tick mark every 10 PSIs. Actually, no, it's every 5 psis, right? 60, 70, 80. Every 5 psi. So I could estimate roughly to the single place. So like I could estimate 71 psi, 72 psi. Let's say that I measure using this device and I get that the tire pressure in my bike is 76 psi. Okay, that's great and all, but I decide I want to see, is that really what the pressure is? So maybe I'm buying this tire and it says on the side of the tire that it exactly has 75.45 psi in it. Okay, so this is the exact answer. This was the observed or measured answer by us. We can use another calculation that we can do in this class, which is to figure out what the percent error of the measuring device is. And the percent error, or my observed measurement, percent error is the actual measurement, divide the actual, what I think it is, so the exact measurement here, and minus the observed value, divided by the actual times 100. So in our case, that actual value, or what it should be, is 75.45. My measured value that I measured just now was 76 psi. And I divide that and I multiply by 100, and I get that roughly it's, well, 0.0728959% off from the actual value. Now, I also want to point out a thing here. So you're going to get a negative percent value. That's okay. That just means the order here has flopped. You can just make that positive. The negative sign is not important here. We just want to know the percentage. Now, of course, this would be a ridiculous answer to record because I know that in terms of significant figures, my device did not measure to this significant, so there's no way that the percent can be that accurate. So I need to base it off of one of the operations. Now, this is a mixed operations problem. So we just talked about multiplication. Multiplication means the least number of significant figures. If I'm doing addition or subtraction, that means that it's going to be to the lowest number of decimal places. Well, in this case, I have subtraction and a division. I'm going to base it off solely the arithmetic in terms of the addition or subtraction. So here I have 2 decimal places and here I have 1 decimal place, which means my answer should only have 1 decimal place in terms of significant figures. That means that this number is going to round to 1%, which means I'm pretty good that my measuring value was 1% or percent error. Well done, Velociraptors. Now, hopefully you understand what we're talking about when we say significant figures. It tells you the actual accuracy of your measuring device. Now you understand when I'm recording significant figures, I need to record it 1 past the tick mark. That's my uncertain digit. I know that when I'm using subtraction, I need to ensure that I'm maintaining significance based on decimal places. If I'm doing multiplication, I would record my answer based on the least number of significant figures. And if I have a combination of subtraction or multiplication, similar to the percent error calculation, I would then record my answer based on the lowest accuracy decimal place in my measured values. Great work, Velociraptors. Good luck.